In this lesson, we'll consider another example of sketching a graph of a function using our guidelines. So remember our guidelines for sketching a curve y equals f of x. So we find the domain, intercept, symmetry, asymptote, sign, intervals of increase, decrease, max and min values, and concavity and points of inflection. Our graph here, our function here is f of x equals x squared over the square root of x plus 1. So let's start with domain. So the domain is, we have a square root in the denominator, so x plus 1 needs to be positive, which means x is bigger than 1, which means our domain is the open interval -1, infinity. What about intercepts? Well, when x is 0, y is equal to 0. So 0, 0 is our y-intercept. And if we looking for x-intercepts, we set f of x equal to 0. That gives us x is 0, so 0, 0 is both our x-intercept and y-intercept. Looking for symmetry, so let's plug in f of -x. F of -x is -x quantity squared over root -x plus 1. That's neither f of x nor -f of x, so this one has no symmetry. What about asymptotes? So the limit as x goes to infinity of x squared over root x plus 1 is infinity. Now we don't need to worry about the limit as x goes to negative infinity, right? Because our domain is only -1 to infinity. So we have no horizontal asymptote because the limit as x goes to infinity of f of x is infinity. What about vertical asymptotes? Well, we know that our denominator goes to 0 as x goes to -1 from the right. I can't look at x going to -1 from the left because that's not in the domain of our function. Moreover, note that f of x is always positive, right? X squared over squared is always positive, so that the limit as x goes to -1 from the right of x squared over root x plus 1 is positive over something going to 0 that's positive, so plus infinity. This tells me that x equals -1 is a vertical asymptote. Next, let's move on to the sign of f of x. Well, we just argued that f of x is always positive for all x in the domain, so we don't have to worry about sign changes of f. So we'll go on to intervals of increase and decrease. We need to get the derivative of f. To do that, we'll use the quotient rule, right? So we get the derivative of the top, which is 2x, times the bottom, minus the top times the derivative of the bottom, all over the bottom squared, which is x plus 1. And now, since we have to work with that thing, I've said let's do some algebraic simplification. So what I just put in parentheses is what you get when you just take the derivative, of course. So let me erase this stuff on the outside. So this is what we get when we take the derivative of f. Here's our f prime. But now, as I said, I'm going to have to work with this. So let's go ahead and multiply top and bottom by 2 root x plus 1. That will get rid of that fraction in our numerator. And so go ahead and do that simplification and you'll see that you get f prime is equal to x times 3x plus 4 over 2 times x plus 1 to the 3/2. So where could f prime possibly change sign? Well, f prime could change sign when it's equal to 0 or when it does not exist. F prime is equal to 0, obviously x equals 0, -4/3. Now -4/3 we don't have to worry about, right? Because that's not in the domain of our function, so we don't have to worry about that one. And f prime of x does not exist at x is -1, which is also not in the domain of our function. So our intervals are -1, so x in between -1 and 0, and x bigger than 0. So again, we're just looking for the sign of f prime and what that tells us about f. If x is in between -1 and 0, x is negative, 3x plus 4 is positive, x plus 1 to the 3/2 is positive, so f prime is negative, so f is decreasing. If x is positive, then everything in f prime is positive, so f prime is positive, so f is increasing. So f is decreasing on the interval -1, 0, and increasing on the interval 0, infinity. Critical numbers, our only critical number was x equals 0. Remember, x is -4/3 and -1 were not in the domain, so they're not critical numbers. At x equals 0, f prime changes from negative to positive, which tells us that 0, 0 is a relative minimum. So our function changes from decreasing to increasing at x equals 0, so we have a relative minimum there. Okay. So now we have our intervals of increase, decrease, and our relative max and min. So now we just need to deal with concavity. So we need to take the second derivative. So that f prime was itself a quotient. We'll have to use the quotient rule again. When you're taking the second derivative, it's probably useful to write this as 3x squared plus 4x over 2x plus 1 to the 3 halves. And now we just, when we take our derivative, of course, we get derivative of the top, which is our 6x plus 4 times the bottom, minus the top times the derivative of the bottom. And we get, sorry, of course, this should be times 3 times x plus 1 to the 1 half, sorry about that, all over 4 times x plus 1 cubed. Again, go ahead and do your algebraic simplification, and you will see this becomes 3x squared plus 8x plus 8 all over 4 times x plus 1 to the 5 halves. So when is f prime equal to 0? Well, we just set the numerator equal to 0. We get, using the quadratic formula, negative 8 plus or minus the square root of b squared minus 4ac. 64 minus 12 times 8, that's 64 minus 96, that's negative, so we have no solutions there. F prime does not exist at x equals negative 1. Again, negative 1 is not in our domain, which means we have the same concavity for all values of x. So basically, f double prime never changes sign on our domain. So let's figure out the sign of f double prime. We know it's the same no matter what x value we're in at our domain. So we can just plug in any number x. So for example, if we plug in x is 0, that's in our domain. F double prime of 0 is positive. So it looks like it's 8 over 4, which is 2, which is positive. We just argued that f double prime never changes sign, so f double prime of x is 0 for all x in the domain of f. So our function is always concave up. So thus f is concave up on our entire domain, and we have no inflection points because we never change concavity. Using this information now, we can go ahead and sketch our graph. So let me pull up a clean slide. So how are we going to sketch our graph? So remember, our domain is -1 to infinity. We know that as we approach -1 from the right, our function is going to positive infinity. We know that 0, 0 is a min. We know we're decreasing to 4, so let's look at our intervals of increase and decrease again. We're decreasing on -1 to 0, increasing afterwards. 0, 0 was a minimum. And we know that our function is always positive. And we know that we have no horizontal asymptotes, so as x goes to infinity, f of x is going to infinity. We're always concave up. Putting all of this together, we get the following sketch for the graph of f of x. So this is our sketch for f of x equals x squared over the square root of x plus 1. Again, just to summarize, the key information from this series of lessons for sketching a curve y equals f of x, run through your guidelines checking domain, intercept, symmetry, asymptotes. Of course, this should say limit. There should be an f of x here. Sign of f of x, intervals of increase, decrease. Remember, you're looking at f prime there. Local max and min values, that's where you're looking where f prime is equal to 0 or f prime does not exist. So you're checking your critical points. Concavity, you're using f double prime.